to 60. If you were wondering where Jim was, I guess George has explained this here for us. He is here now. I do have a couple details I want to start off with. So first of all, there are some people that have not yet registered. So at the break, it's registration and coffee. So it's an inducement. And coffee is in 110, which is just through the doors, 2 sets of glass doors, and then in the room behind the elevator bay. Okay. And also I'm told by Marvin that some people have not yet paid for dinner. If you haven't, he's going to take your money or your life at coffee. Okay. So I just say a few words to people who weren't here for the CITA 25 part. We did have a huge turnout, about 180 people registered, probably a little over 200 were here. Okay. And there are of order 60 or 70 former CITA postdoctoral fellows. And I tell you this because it's clear that people, while they were here, did a great job on science and were very productive, but they also enjoyed themselves. And one of the reasons for that, of course, was that Dick was at CITA. Dick and Scott, I should say, really set the tone. I mean, we've always had great science coming out of CITA. That's a legacy of theirs. Another one is, of course, that people like to have a good time. And Dick certainly embodies that. He's also a bit obsessive at times, as you may have noticed. He gets a little worried about details sometimes, which are not necessarily that important. I'm not quite sure why he was really late this morning, but I suspect he was running around in panic.
Karen has a ride with us.
Okay. But you could have left early. So one of the things that I recall very well, I'm not quite sure who started it, may have been actually Dick, but Dick has been running Cosmo Beer for more than a decade, maybe 20 years. That's certainly one of the things that people at CITA remember well. Just wait a minute, somebody's not happy in the audience. You notice though, John is also late. This is probably a learned behavior. Anyway, just I can point out that my actions do speak louder than words. I can tell you that Dick has created a great atmosphere in Toronto CITA over the last 25 years, along with Scott, of course. But actions do speak louder than words, and the fact that so many CITA postdocs come back really does tell you that people enjoyed their stay here. Okay. Well, since we're starting later, I think I'll just stop there. Oh, I will say one other thing, of course. Besides Cosmo Beer, Dick's also very famous for his love of wine. And that may be, of course, why some of you came here. You're aware that he probably took some care in selecting the wine tonight. And we'll see how well he did. But I can tell he did put a lot of effort in. So with that, I'll turn it over. Peter is chairing the session. And he can, well, actually, George, may as well just get up and start.
Thank you. Well, I wasn't joking. It really is a lander, Dick, and I'm not going to let you go until you admit it. If, like me, you try to find the program and Google Pondfest, you've got something like this. Unlike one of my postdocs who Googled Dickfest, you get a very different. Of course, I'm a great fan of Dick. I regard Dick as my closest collaborator. And what I'm going to talk about some of the stuff that we did. We wrote 15 papers together. We started in 1980. And here they are, ordered by a number of citations. And as I said to Carlos many years ago, if you want to get citations, it's not the intellectual quality of the paper that matters, it's whether it's useful. Find some fitting function or something. So I'm not going to talk about this. So what I'll do is I'll start from the very first paper that we did, pick some things. We started in 1980, and the last paper that we wrote together was in 1999. And even with close collaborations, after a while you end up with departments to run. Dick has his citizens, I have my cavaliers, and you have families and so on, and so naturally collaborations wane. But while we were working together, it was great fun. This was what Dick was like when I first met him in 1979, and we met at Berkeley. We were both postdocs there, and that's when we started collaborating. So isn't that cute? The last time there was such a close Dick and George collaboration led to a war in Iran. So we collaborated so closely that we used to sit at separate desks and derive stuff and then compare results to make sure that we got them right. It wasn't just all work, there were trips and things. This is Ray Carlberg. And so we had lots of fun as well, including the infamous trip to Paris, of which we never speak. Don't you dare say. And since there are so many friends from those days in the audience, I decided to put this picture in. Dick's not here, but this was from a few years later when we were doing the whole dark matter simulations. This is Mark Davis. There's Simon. He's now dyeing his hair. And, Carlos, who was actually lost weight. And for some reason, this is quite a typical picture. Joe was always lurking somewhere. So, this was the first paper that we wrote together. And this arose, Dick was working on supernovae at Berkeley. And I was talking to Mark Davis over the phone. And he said, have you heard about this result? It's a reported measurement of a 48 electron volt neutrino. I said, no. So I walked into Dick's office and said, do you know anything about this? And he said, no, but I'll make some phone calls and find out. So he got the background of the Russian experiment. And so we started thinking about, what this would mean for structure formation. And this was the result. Of course, what we calculated was the characteristic scale for free streaming of neutrinos of a given mass. And
30 would be 1,000.
In people's notation. this is our notation. You made me lose my train of thought. Okay, we argued so much about this question. Okay? We calculated the characteristic scale, and I wanted to write it from a negative point of view, that this didn't match observations. It would mean that the scale of structure would be too large, galaxies would have to form from pancakes and so on. And I wanted to write it from a very negative point of view. Dick, was more sensible and decided that we should just present it in a fairly neutral way, which is what we did. But we worried a lot about this stuff, and we also so we didn't just look at adiabatic perturbations. We also considered isocurvature, dark matter perturbations, and we also thought about what would happen if you had heavy particles, heavy nuclear interacting particles, and that was a way of bringing this mass scale down. So there's actually quite a lot of stuff in that paper. And of course now we know that neutrinos really do have a mass, and this shows you the various possibilities for atmospheric neutrino and solar neutrino experiments with normal hierarchy, inverted hierarchy, and of course if the absolute mass of neutrino is high, then they're degenerate. So the picture that you get is there should be a detectable neutrino mass. There should be a neutrino mass of around 0.06 eV or greater. And the best way of proving that sort of mass range is cosmology. And this is a figure from a paper combining WMAP and other CMB results with baryon oscillations and measurements of the Hubble constant. And you can see that the different data sets give you some upper limit of around 0.2, 0.3, or somewhere in that region electron phase. And as Wendy said in the very first talk at this meeting, that if you can improve the precision of H0, for example, then you will tighten these constraints. So, this is, I mean, it's interesting, we did that work on neutrinos. I think that was the first time that in the Western literature, at least, the link between the nature of a particle and structure formation is first discussed. And cosmology still seems to be the best prospect for constraining and possibly detecting neutrinos. So, in the late 80s, early 90s, I was working on structure formation, and this shows the AIM survey that we did at the time. We did various redshift surveys based on IRAS and so on. And this shows the angular correlation function, CDM model with lambda equals 0, and a CDM model with a cosmological constant. And that was my favourite explanation of the data at the time. And I was invited to go to Downing Street and discuss this, present a talk on this stuff to Margaret Thatcher in 1990. And I showed this stuff and gave this explanation. And a few weeks later, Margaret Thatcher resigned. This was such a horrible she couldn't possibly carry on this. So Mrs. Thatcher was not the only person that was unimpressed by this. Then Dick said, come on, there are many ways of explaining excess large-scale structure. And so with Jim Bardeen, we co-wrote this paper with a typical Dick table. Here's the lambda CDM model with lambda equals 0 and various measures of large-scale structure, correlation functions, velocity, bulk flows, temperature anisotropies, which hadn't been measured at that time. This is the lambda CDM model, and there are many others. Isocurvature cold dark matter combinations, hot and cold, mixed dark matter models. Do you remember what these models? Do you do? There's even CDM. So this is CDM with a decaying particle, decaying heavy particle. This is CDM plus X, and the X was just a bump in the spectrum to explain large-scale structure, and the referee allowed this. So it shows you, Dick's imaginative powers. But I'm saying for Dick, it is this. This paper, I think, is responsible for holding back the field by at least 6 or 7 years. Anyway, I think the most, from my point of view, the most satisfying, significant paper that we wrote together was this one, where we set ourselves the goals of calculating fluctuations in the CMB as accurately as we could, valid on all angle scales for adiabatic and isocurvature models. And these are some of the results. acoustic peaks, temperature, and polarization as a function of wave number and then projected onto multiple lumps on the sky. And in this paper, we did a very simple thing of constructing images on the sky. And so this was a realization of an adiabatic fold-up matter model in a 10 by 10 degree patch of the sky. And nowadays nobody bats an eye at these kinds of we use them all the time. But at the time, when I gave talks and referred to, said it was a simulation of the CMB, people didn't know what I was talking about. They were sort of confusing it with n-body simulations. And so I was, had to explain very carefully that it was a Gaussian field generated from power spectrum with computers. So when we did this stuff back then, did you ever think that we would see images of the CMB like that? There you go. It wasn't so sure. It's remarkable that this stuff has been detected. We also computed the polarization pattern, and we got this wrong. Okay, so that was a realization of the polarization pattern on the sky. And what we've missed, for some reason, we've missed the correlations between temperature and even polarization. And we just weren't thinking we was really focused on the temperature analysis, and we didn't think carefully about the polarization pattern. But we knew it right. So, remarkably, that's what we now see. So all of this stuff is observed to high precision, and it fits the simple adiabatic model with a mean-scale invariant spectrum. So remarkable progress we have learned over the last 25 years or so that we don't understand 96% of the universe. So there's plenty more to do in cosmology, and after, more or less after, we did that sort of work, we got involved in the Planck proposal, which started off in 1992. This is a picture of CoBRAS. Planck was the merger of two proposals, CoBRAS and Sandler. They were proposed in 1992. Planck was selected in 1996, and it was launched a year ago. Yesterday was the first anniversary of Planck's launch. So it was 16, 17 years from proposal to launch. And during this period, our collaborative papers were basically on prospects for determining cosmological parameters for Planck, and they were related to the Planck sampling. So Planck was launched. Dick and I went to the launch. So this shows Ariane 5, and inside the fairing, there's the Herschel infrared telescope, and Planck bolted on underneath. And this shows the launch of Planck from the distance that we were at. And the third picture shows, I'd never seen a launch. I wasn't prepared for what happened. If you ever get an opportunity to go to a launch, take it, because it's really unlike seeing it, on a computer screen. It's just this amazing explosion, and off it goes. And then from where we were standing, it went up, and then sort of turn down. This is an optical illusion, but I wasn't prepared for it. So it started to go down. And then, at around this point, it ejected these boosters. And once it ejected the boosters, there was this kind of little crackle and pop, and it was gone. I turned around to Dick and I just said, "Oh, that's that." What have we just seen? And I don't think Dick was too sure either. He didn't seem confident. So we went off to the monitors to see what was going on, and the rocket was absolutely bang on the right trajectory. So we were happy. So here we are, just after launch, and inflation was discovered in the 1980s, and both Dick and I duly inflated. And this is me on the phone to Cambridge, where they broadcast the launch in the lecture theatre there, saying, "It's okay, it's okay." And they said, "We know it's okay." What did you think had happened? So anyway, this is a terrific. I think this is a terrific shot because 27 minutes after the launch, Planck and Herschel separated, and this shows pictures from a camera on Herschel, and it shows Planck in its carbon fiber cylinder. This is Africa in the background, and at that point, Planck was detached. The cylinder was ejected. Planck was spun up, and that was it. And it was off to LT. And at the time that Planck was injected into its orbit, the velocity of injection was accurate to a fraction of a percent, which is incredibly impressive, and they regularly achieve that kind of precision. Once Planck was on its way, it was amazing. Some of the scientists there, people that had worked on the instrument, actually burst into tears. It's a very emotionally intense experience. So, what is Planck designed to do? Here are simulations of what we expected from Planck at the different frequencies, running from 30 to, in this bottom, 30 gigahertz to 340 gigahertz. That's with the noise subtracted. And what I think I can say, Francois will shut me up, is the real data look very, very similar to this. I'm not going to show any real data, but Francois will show some real data. It's amazing that complicated satellite is working flawlessly. So after the COVID results were announced, Dick, Simon, and I wrote a little paper on interpreting COVID. This shows a letter that I wrote to Martin, Simon, and Dick, because Martin had said, "What about gravity waves?" And so what I did in this letter was just look at the tensor scalar ratio for parallel potentials, and the conclusion is that unless the potential is incredibly steep, gravity waves were a small component. And we should have just published that, more or less as it was. But within a year, we'd done a very detailed calculation of the tensor modes. And again, we were so focused on temperature that we calculated the polarization pattern, but didn't project it onto the sky. It just didn't project it onto the sky. So we missed the E and B decompositions, which of course are now a major goal for CMB experiments. So let me just show you some simulations of what we think Planck do. So here are Q and U maps on the sky. So this is degraded to 10-degree resolution, and with a sky cut imposed. So that's theory. And that's what we think we can extract from Planck. But we'd like to isolate the B mode. That's what we think we can do with 2 sky surveys. And Planck has been approved for mission extension, so we should get at least 5 sky surveys from Planck, as long as it's working. And that's what we think we can do with 4 sky surveys. So compared to theory, that's for a tensor scalar ratio of 0.1. So Planck has the sensitivity to do that. What we don't know yet is whether we can control the low frequency noise properties and polarization systematics to be able to do this. That is at the edge of what Planck can do. But Planck intrinsically has the sensitivity, and I'm also firmly convinced that the polarized foregrounds control. But if Planck doesn't succeed in doing this kind of science, Dick is lucky enough to have a second shot with Spider. So Dick's in a very fortunate position. So Dick has introduced some vocabulary that we regularly use. I think he was the first to introduce cold, warm, hot, dark matter into the cosmic lexicon, the cosmic web. A lot of the notation that is commonly used came from Dick, and people have me to thank for removing some of the superscripts and subscripts. There's gastrophysics, and when we were writing one of the Planck papers, I wanted to call it something like the prospects for determining cosmological parameters with the proposed Planck satellite, assuming that it launches satisfactorily, something like that. And Dick said, let's just call it forecasting parameters from Planck. And I said, forecasting? That's horrible. And anyway, Dick won that battle, and forecasting has become part of the language, and I'm very glad that it has, because now if I see a paper on AstroPH which has forecasting in the title, I know not to read it. That's a really useful contribution to the field. But the phrase that I most associate with Dick is this. That's quite a typical Dick reaction while we were collaborating. So here went through the ADS, and this shows Dick's publication record. So it's plotted year by year in silk units. Okay? And a silk unit is 10 papers per year. I introduced this unit for Joe's 60 group. You can see that, and in Dick's case, in Joe's case, his publication record varies between around 1 and 2.5 silk units. And curiously, it anti-correlates with the solar cycle. I will let Glenn start when it turns. So, anyway, you can see Dick has seeded a silk unit once. He got very close the second time. But the interesting thing is that the overall trend is upwards. So we expect more from Dick. Now, I said that our last paper was in 1999, and that's not true. Strictly true. This one has been accepted for publication. It's the first paper that we've written together since then. There is me. You can see, I mean, it's an indication of how our subject has changed over the last 30 years. We have, just this massive audience. The research is very different now than it was back then. But the BE collaboration is set to continue, and so the bondage really does carry on. So, anyway, I've given a summary of some of the things that we've done, some of the impact that it's had. As I said at the beginning, I regard Dick as my closest collaborator. It's not just the science, but it's the human bond that is important. And long may it continue. So happy birthday, Dick.
Questions, comments?
What happened in Paris?
Totally classified. At which time?